Hello and welcome to my free CCNA Cisco Certified Network Administration course. And today we are going to be talking about spanning tree protocol. So our objective for today is we are going to understand what is STP and why do we need STP, how does it prevent looping, and then we are going to understand the nitty-gritties of it, the how the root bridge is selected, how the root port is selected, how the designated ports are selected, and which port is blocked. Then we are going to understand the different states that the ports go through while converging and what is the time that they spend on those states and what happens to the STP during that time. And in the end, we are going to understand what are some of the security issues that STP may have. So let's get into it. And first, let's understand why do we need STP. So let's say our network has three switches, switch 1, switch 2 and switch 3, and there is a client connected on switch 3. Now it wants to send certain data to a client on maybe on another switch. We don't know which switch it is. So what happens on switch 3? Switch 3 broadcasts uh, the frame to all the ports other than the port on which it's receiving, right? So it's going to broadcast here and it's going to broadcast to 2 also. So now what happens when it reaches switch number 2? When it reaches switch number 2, again, the broadcast happens because it doesn't know the MAC address of that client. So it's going to broadcast on all the other ports other than the ports on which it received the data. So it's going to broadcast from here. And what will happen on switch number 1? Again, the same thing is going to happen and it's going to broadcast to switch number 2. Now, when switch number 1 receives the broadcast on switch number 2, that had originated from 2 now. So it came from 3 to 2 and 2 sent it to 1. So what's going to do with that broadcast? It's going to redirect that broadcast to switch number 3. And what is going to happen to this broadcast that has come from 1 to 2? It's going to broadcast to switch number 3 again. Now, what is going to happen is this broadcast is going to loop both ways on all the switches. It's just going to broadcast, broadcast, and broadcast. So it's going to broadcast from here. Again, switch 3 receives a broadcast from switch number 2. It's going to broadcast it back to switch number 1. And switch number 1 is going to broadcast to switch number 2. And this is going to go on. The switch number 1 broadcast that is coming from to switch number 3 is going to be broadcasted to switch number 2. And again to switch number 1. So what is happening is there is now a loop in the network. Nothing else is going to happen. The MAC addresses are going to be unstable and the communication is pretty much dead. So what does STP do? In nutshell, STP prevents loop from happening. But how does it do it? So it follows a certain steps, it follows a certain procedure for a network to not get into. The technical aspect of it is the first step is it elects a root switch. Now, this root switch is going to be controlling all the other switches. Once a root switch is elected, all of its interfaces are placed in the forward state. That means all the ports are forwarding the data, all the ports are forwarding the packets, and nothing is blocking. Step 2 is all the other non root switches, that is, will calculate their cost to the root switch from all of their ports. And the port which will have the lowest cost is going to be named as the root port. And that port is going to be placed in the forward state. The next, what is going to happen is that some non-root switches are going to be connected to another non-root switches, and whichever switch will have the lower root cost on that segment will become the designated switch, and its port is going to become the designated port. Whatever ports are left after that are just going to be put into blocking state. This way, the loop in the network will be avoided. So, how is root bridge elected? To elect root bridge, a certain criteria is followed. The criteria is pretty simple. The switch which has the highest priority is going to become a root bridge. By default, this is set to 32768 in all the switches. You can obviously change this, but by default, it is 32,768. What if we don't change it? What happens? Well, each switch has a unique MAC address. So you guessed it right. The switch with the lowest MAC address is going to become root bridge. Now going forward, you will understand this, that leaving to MAC address is not a good option. Why? Because the older manufactured switches, that is the switches which have become old now, will have lower MAC addresses. And because they will have lower MAC addresses, become root bridge, and that means they will be using more CPU on them. Definitely, we don't want that to happen. So the best thing is we work on priority. Now, priority is to be set in increments of 4096. So this priority is divided into two parts. So it has to be set in increments of 4096, that we understand. But there are two parts to this priority. The first is what we can manually set, and then there is something that we get because of VLAN. So essentially, this priority part only forms the 2 byte data of the bridge ID. Now, this bridge ID is with all the switches which are broadcasting into the STP domain. So the priority part, this part that you are going to manually set, that is this, versus the VLAN is going to be the other part. So as I told you, priority is 2 bytes, that is 16 bits. And if you remember, VLAN is 12 bits. So the other 4 bits is what you can send manually. Now, if you were to look at this, VLAN 0 to 4095, what happens to the next one? 1 comes here. So essentially, if 1 is here, this becomes a value of 4096. So priority 0 being the highest, next is 4096, and the next is 8192, and so on so forth. The last being 61440, all ones, and VLANs all zeros. So this way, with priority, you can define manually which switch will become the root bridge. Obviously, the lower the priority, the better it is. So now we know that bridge ID forms the important part of formation of the root bridge. The priority is the first part of this bridge ID, which is 2 bytes. The next is the MAC address, which is, yes, 6 bytes of data. So this bridge ID of 8 bytes is going to define which of the switches is going to become the root bridge. So what happens in a scenario like this? So in a scenario like this, let's assume that all the switches were right now off and they had been put on. And all of them have a priority of a default, that is 32768. We are not changing this right now. So switch 2 gets on and it says that I am the root switch, and switch 2 is not wrong. This is what happens with all the switches when they're switched on. They assume themselves to be the root switch or the root bridge. So the switch 2 sends a BPDU, that is the bridge protocol data unit, hello to all the other switches, and it says that I am the root bridge. Now, switch 1, when it receives this BPDU, it sees that the bridge ID is inferior to what the switch 1 has, and it drops that BPDU and assumes itself to be the root bridge, and retransmits the packet to all the other switches. But wait a minute, switch 3 also received switch 2's BPDU, saying that switch 2 is the root bridge. So for switch 3, this is a superior BPDU, it's a superior bridge ID, and switch 3, what it does is it immediately updates it, and the root bridge is updated as switch 2. So right now, the root bridge at both switch 2 and switch 3 is switch 2, and on switch 1, it is still switch 1. Now, switch 1 broadcasts and the BPDU of its own to both the switches. Let's change the color so that we understand this. And it transmits a BPDU of its own. Now, switch 1, when it transmits this BPDU, this switch, when it reaches switch 2 sees that this is a superior BPDU, so it stops assuming itself to be the root bridge. Now, the new root bridge for switch 2 is switch 1. Similarly, for switch 3, when it receives a superior BPDU, it stops assuming that there is another, the switch 2 is the root bridge, and the root bridge becomes switch 1. This is in the most simplest terms one can explain you how the STP convergence is happening, how the root bridge is getting elected. Now, if this were to happen before switch 2's BPDU, which was sent to switch 3, and switch 1 BPDU was already there, then switch 3 would have simply dropped switch 2's BPDU and retransmitted a fresh BPDU of its own, saying that there is a superior switch in the network, and that's switch 1, and that's the root bridge. So this is how the root bridge becomes the master of the domain of the STP. So we have done the first step of the process. Our switches have elected their root switch, and all the ports on the root switch, as I've already told you, will be put in the forward state. The second step now is a root port has to be found on all the non-root switches. So let's see how that happens. So understand how the root port election happens. What we need to understand is that each port by default has a certain cost. So there are two methods with which the cost is calculated. The old method is good for only up till 10 gigabit ports, but now with the advent of the 100 gigabit and the 1 terabit port, the old cost method does not appears to be good. New method is the better one. To calculate the new cost method is very easy. All you need to do is divide 20 million by the port speed. So for example, 10 Mbps port, you divide it by 10, 100 Mbps, you divide it by 100. For 1 gigabit, you divide it by 1000, and so on and so forth. The old cost method, you will have to remember a bit. So let's understand how does this cost come into play. So our switches have already decided that switch 1 is the root bridge. So a root bridge, the cost is going to be 0 for all the ports associated with this switch. So the cost is going to be 0. And we assume that all the other ports are gigabit ports. So this port is a gigabit port. This is also a gigabit port. This is also a gigabit. And by default, we have seen the old cost method. The cost of the port is 4. Now, for switch 2, there are two paths available. One path is from here, and the other path goes through switch 3. Now, the path that goes directly, the cost for that path is 4, and the cost for the other path is 8. So 4 for going from here, and 4 from going out this port. So 4 plus 4 is 8. So definitely this gigabit port that is connecting between switch 2 and switch 3, it doesn't make sense. So the port that is directly connected with switch 1 is given the root port status on switch 2. So this will be given a root port status. Similarly, on switch 3 also, the directly connected port will become the root port. Now there are some cases where more than one port can become a root port. Now in those cases, the tie is broken by 3-step process. The first is the lower bridge ID on the neighbor will become the root port. This is only in the case if there are multiple ports which are having the same cost to reach to the root switch or the root bridge. The second, even if they are connected, both the ports are connected to the same bridge ID, that means both the ports are connected to the same bridge. In that case, a lower port priority on the neighbor switch will become the root port. So if that is also not there, then the internal port number of the neighbor, whichever is lower, connected to the lower port, will become the root port. So that is how the tie for the root port will be broken. So by default, as I told you, these port costs, and by default, what is going to happen is that the Cisco switches is going to use the old cost method. To change this, what you need to do is in the global command menu, you need to enter the command spanning tree path cost method long. If you use that, it will use the new cost method, but make sure that the path method that the cost method that you are going to use is going to be the same across all the switches in the STP domain. Now we come to the third step of the process. And what we need to determine now is there are two non-root switches, that is switch 2 and switch 3, which are connected to each other. So which port is going to be the designated port and which port is going to go into the block state? So again, this is determined through a process. The first step is whichever switch is pushing a hello with the lower cost towards root bridge will become the designated port, owner of the designated port. But in this case, both the switches are connected to the root bridge with the same cost, that is a cost of 4. So the hellos give out that we are both connected to the root bridge with cost 4. That makes no sense. So both are same right now. So the second tiebreaker becomes here is which of the switches is broadcasting a better bridge ID. So in this case, switch 2 is broadcasting a better bridge ID. Therefore, this port will become the designated port and this port will go into block. Again, this is a step-by-step process. If there is a better hello going from one of the switches to the other switch, saying that I can reach root bridge at certain cost. So if the cost is lower, that switch will assume the designated port. If that's not the case, both the switches have the same cost, then in that case, the one with the better bridge ID is going to become the designated port. So how did the blocking port came into being? We are left with only the last option, that is the step 4. Whatever is not the root bridge, whatever is not the root port, whatever is not the designated port will become the block port. So in this case, the switch 3 port connecting to switch 2 becomes the block port, and the switch 2 port connected to switch 3 is the designated port. Now this whole convergence has some times associated with it. The first and the foremost is the hello timer. That is, every 2 seconds, the root bridge is going to send out the hello BPDU to all the other switches, and all the other switches are going to send it forward on all of their ports, telling that the switches are still there and the root bridge is still alive. And there is a max age, so this is not going to be happen indefinitely. The switch is not going to wait for the BPDU from the root bridge indefinitely. This BPDU, this has a max timer, and that max timer is 10 times the hello timer. So for 20 seconds, if the switch does not receive any hello packet that is from the root bridge, then it assumes that it has lost connection and it needs to converge again. Now, when this convergence happens again, there are some forward delays. That is, the switch goes into the listening state and the learning state, and during each of these state, there is no forwarding of the packets that is actually happening, and the port are either listening or learning the MAC addresses, and each of the state has a default time of 15 seconds that they must converge through. But in the listening state, all these tail MAC addresses that are there in the switch's MAC address are dropped. So when the switch loses communication with the root bridge, the first state that it will enter is the listening state, and in the listening state, it will block the packets from coming in. It is only going to be listening to the BPDUs. From listening state, the switch converges to the learning state, and in this state, the switch starts to learn the MAC addresses once again. It is still not forwarding any packets. It's still not forwarding any frames, and the traffic is pretty much stopped right now. So once all this convergence happens, then the switch either goes into the forwarding state or the blocking state, whatever state we have just discussed, it enters, and once it's through there, it starts to forward the frames, forward the data packets again. Now, each of these states that the switch has been going through uh, will either not forward the data frames, or will be learning MAC addresses, or will be a stable frame or a transitory thing. So blocking in this, no data frames are transmitted, nothing is learned, and but this is a stable state. That means it's not going to be fluctuating from one state to another in this state. But when it is in listening and learning, there is no forwarding of frames happening in both, but in learning, it is at least learning the MAC addresses. But both these states are not stable state. These are only transitory state. It will remain in this state only for 15 seconds, and after that it is going to again change state. Now in forwarding, it forwards the data frames, it learns the MAC addresses, and this is the stable state also. If the switch port is disabled, then nothing is going to happen, but this is again a stable state. So if a port goes down in a switch, say our current scenario, if the port between switch 1 and switch 3 goes down, so there is a chance that the switch 3 will go up through switch 2, but this can take up to 50 seconds. That is, it's going to wait 20 seconds first for the max H timer to expire, then for 15 seconds for listening state, and then 15 seconds for the learning state. So probably for 50 seconds there is going to be an outage at switch 3 end. So this is not something good. The customers or the clients connected to the switch 3 can really suffer in this scenario. So to overcome these limitations of the STP convergence time, which is very big, we have some strategies. We can use Ether channel. Ether channel is basically we are pooling two or more interfaces as a single link. So the whole premise of STP is that if there is a link failure, there is a redundancy. With Ether channel, what we are having is multiple links are going to the same switch, and they are all being treated as a single link. So if all the links fail, then only STP convergence will take place. Otherwise, STP convergence will not take place, and Ether channel will manage the problem for us. The second thing is port fast. Now, port fast is a feature that is used primarily between a switch and an end client. Because we know that there is no further switch connected to it, and we know that we are not going to receive any BPDUs. So we can switch on the feature of port fast on that particular port, so that there is no convergence. If we are removing say a laptop which is connected directly to the switch and we are plugging it back in, we don't want to wait 50 seconds. We can have that port as the port fast port. The last option is we can use RSTP. So what is RSTP? We are going to understand in the next session, that is the upcoming session for CCNA. But right now, what we need to understand is that these are the three strategies that we can use. Now, with the STP comes, there are certain issues also involved. That is, an attacker can connect to the switch with lower STP priority and can become a root switch. Now, this new topology could have a lower performance and could not give us the desired results, what we are seeking from our STP domain. The attacker can also plug into multiple switches and become root, and can flow the traffic to their switches, can use an analyzer to copy, to reproduce data frames that are being sent through LAN, and this can really become a security issue for our enterprise. The last security issue is that the customer could be using an inexpensive switch to connect to the network. The switch is not has an STP capability, and such switch can cause loop into the customer network. And because the switch does not has an STP capability, it can cause problem in the network, not only its own network but our network also. So to safeguard ourselves from this, what we can use is a BPDU guard feature of Cisco. As the name suggests itself, it will help the network from blocking ports. If there is an BPDU sent, the port will be blocked. We don't want certain ports to have BPDU sending us BPDUs, like for example access port. So if we are assigning a port as an access port, that means that there is an endpoint client that is going to be connected to it. So there is no point of BPDU being sent on such ports. So BPDU card is what we can use to overcome these simple security issues in the network. So thank you for watching my video today. I hope that you understood STP better with this. In the upcoming videos, we are going to be learning about RSTP, and we are going to be doing a hands-on STP lab in which we are going to be determining with few information available which port is the root port, which is the designated port, what is the root bridge in the network. So yes, this is coming up in the upcoming videos. So do subscribe to my channel to get the latest updates on such videos, and do comment below on what you think on this video. Thank you for watching my channel. Stay safe and keep learning. Goodbye.